In this lecture, we'll be covering solid-state chemistry. On the title slide, it gives you an idea of the complexity that this subject can have, and these are some of the different crystal structure, the orders of the crystal structures that can be found. We're really only going to talk about 3 of them in this class to keep it simple. But if you take like a materials engineering class, that can be a whole semester long. You can, spend much more time and go into more detail on some of these. Just a brief overview of what we talked about last time with intermolecular forces. And I think the important part to remember is the relative strengths of them. Okay? Ion-ion, an electrostatic interaction being the highest. Those are 2 full charges. Ion-dipole, which would be a full charge and a partial charge. Then hydrogen bonding and dipole-dipole, those are partial charges interacting with a partial charge. And finally, partial charge dipole inducing a dipole, and then dispersion and the hydrophobic force. Those are the lowest or weakest intermolecular forces in terms of strength. But we did see at the end of the lecture that those are still very important for things like biology. So let's try a practice or review question on intermolecular forces. Okay, so for each substance, we need to identify key bonding and or intermolecular forces and predict which substance of the pair would have the higher boiling point. Okay, so for the first one, magnesium chloride, that's ionic. Okay, so that has very strong interactions. PCl3 is polar covalent. Okay, so the one with the stronger bonds in it would be magnesium chloride, because that where you have the full charge and full charge interaction, and not more of a partial charge with the polar covalent bonds. So the higher boiling point would be magnesium chloride. Okay, if we look at CH3NH2 and CH3F, we have both polar, okay, but only one can if we're talking about its pure substance, only one can undergo hydrogen bonding. Okay, and that's the one that has a hydrogen attached to nitrogen in it, so that's this compound. So that will have a higher boiling point. Okay. C, we have methanol or ethanol, and this one's a little bit hard. They both have hydrogen bonds. The one that's larger, ethane, has 2 carbon groups on it. This is larger, so it actually, along with the hydrogen bonding it can perform, it also has more dispersion forces in it. It's bigger. Okay, so it has more electron cloud to lead to some dispersion forces, and it will have the higher boiling point. You can also think of it in terms of it's just a bigger molecule, so it'd be harder to get into the gas phase. Okay. And then finally, hexane, which is a hydrocarbon of 6 carbons long, or 2,2-dimethylbutane, right? And so that name probably doesn't do a whole lot for you. Let's just draw the structures out of them. 1, 2, 3, 4, 5, 6. So that would be the structure of hexane. At each of these points is a carbon atom. And (2,2-dimethylbutane) was something like that. So you have a molecule that's more surface area versus a molecule that has less surface area. Same number of carbons. And I drew that one wrong. There we go. And so the one that has the more surface area, the easier to stack and the greater those dispersion forces would be in it, that would be hexane. Okay, so those are all the ones that have the higher boiling points. Okay, this solid state chemistry is from the section 6 in chapter 12, so we're going to be skipping the 12.4 and 12.5 here. Okay, solids are divided into two categories. One's crystalline and the other is amorphous. So crystallines have well-defined shapes because they're very ordered molecularly. Amorphous don't really have any orderly arrangement, and so their shapes on macroscopically are pretty poorly defined. A crystal is composed of particles packed in orderly three-dimensional array called a crystal lattice. Okay, so that term just means it's an orderly, you can think of it as sort of a ladder, how there's rungs on a ladder at very even points. That's sort of what a crystal lattice is. It's very orderly and very, its pattern repeats itself. Right. And looking at some macroscopic views of crystals, here are a few of them, and they're all, as you can see, they're orderly, even on a large scale. You can see this with your eyes, right? You can see how well defined these shapes are. So if we wanted to draw a lattice of a crystal, a very simple crystal, we could draw it using, these black dots here and connect them with lines. And this right here would be a cubic crystal lattice. There's something called what we call a unit cell, and that's the smallest point that can be used to define the crystal. And it's that repeated over and over again would give you the crystal. A 2D analogy for the unit cell is shown here in the figure from the book. So like on a checkerboard, for instance, you could make a unit cell shown in the highlighted region. Okay, so the three types that we'll talk about in this class of crystal packing structures. The first and easiest one is just called simple cubic. Okay, and what you notice is you have atoms at all the vertices of a cube, all the corners of a cube. Okay. And so the coordination number for something like this, if you count from, let's just pick this atom, and you count, or I guess you could say molecule as well. You can have a crystal of molecules, but let's focus on atoms. Okay, if you count from this one, it would be connected to 6 other atoms. Another important thing is if we look at that and just chop the atoms off and look at only one unit cell, so that's kind of what this is showing, your space filling blobs for each of these atoms. They're going to be touching each other. If you just take that unit cell part of it and you look, you're basically getting out 1/8 of an atom at each corner. Okay? And you have 8 corners, so in this unit cell, you have 1 atom per that unit cell. The next type is called a body-centered cubic, or BCC, unit cell. It's the same as before the simple cubic, except it also has 1 atom in the very center of the cube. Okay, the coordination number for this now becomes 8. Okay, and that's a trickier one to explain. But it's something, if you count, right, you still have 6 connections to the blue, but you have these, it's surrounded by 8 other purples that you're only partially coordinated with. Okay, so don't worry too much about the coordination number. The space filling model shown here, again, when you look at just the unit cell, you'll have 1/8 of the atoms at 8 corners, so that's 1 atom. But you'll also have 1 atom now in the center. So that atoms per cell, or atoms per unit cell now, becomes 2. Okay, so you can see that the packing in this arrangement is more efficient. The last one we'll talk about is called a face-centered cubic, or FCC. It's also known as cubic close pack or cubic closest pack. Okay, it has, again, the blue are the same as in the simple cubic, but now we have at each face of the cube, we have an atom. Okay. Coordination for this is considered 12. And when you just look at the unit cell, cut the space filling model and cut it, you'd have 1/8 atom at each of the corners again, so that's 1 atom. And then at each face, you have a half of an atom. And how many faces are there? There are going to be 6 faces, 1, 2, 3, 4, 1 on top and 1 on bottom. So 6 faces of a cube times 1/2 atom each, so that'd be 3 atoms. So 3 atoms for the faces, 1 atoms for the corner, and that equals 4 atoms for this unit cell. So this is the most efficient packing that we will see, at least consider in this class. So let's try a practice problem using those designations. For each crystalline solid shown, determine the number of atoms or ions per unit cell and the coordination number. Okay. So the first one, hopefully you can see that the palladium metal, this is the face-centered cubic. Okay, so the number of atoms, again, for the face-centered cubic, you have 8 corners times 1/8 atom each, which would be 1 for the corners. And then each face, there's 6 faces, each face has a half of an atom. So that's 3. So that's a total of 4 atoms per unit cell. Right? You can kind of calculate that each time, or you can just kind of memorize it. Sort of up to you. There's really only 3 of these that we talk about, so not too hard to just memorize it. The coordination number for this one is 12. Okay, for the, excuse me, for copper iodine, this one's a little bit trickier. And so for this one, they're considered both, it's very hard to see the copper in here and how that's arranged. But how it's described in the book is that you have the iodine's face-centered cubic and the copper is face-centered cubic. Okay, so you have changing face-centered cubic or interlaced face-centered cubic. How it looks in the picture, though, it looks like you have a face-centered cubic with respect to iodine, which again would just be, for iodine, face-centered cubic. That would be 4 atoms per unit cell of iodine and a coordination number of 12. The copper, however, that's more difficult to see. And if we're just looking in this picture, it looks like we have 4 complete atoms of copper there. Okay, so if you want to count this as well, we have 4 atoms of copper. I suppose that's, well, the charge probably doesn't matter here. But if it's CuI, it would be copper plus. Right, so that, if you want to say a total of 8 atoms per unit cell, I think that'd be fine. Okay, and then finally, we have body-centered cubic for molybdenum, body-centered cubic. And remember that we have 1/8 at each of the corners and 1 full atom in the center, so that is 2 atoms per unit cell. And the coordination number for here, if you remember, it's 8. Okay. So this figure kind of shows you how you can pack spheres to obtain 3 cubic and hexagonal unit cells, just mentally, if you want to try doing this in your head, right? If you have one layer of spheres and you put another one straight on top of it, you get this simple cubic. That's where that simple cubic unit cell comes into. And the packing efficiency for it's 52%. Right? If now your second layer here is a different color, they use green, you move over one spot so you're not directly on top of each other, the layers, you kind of shift it over into the space, and then you put a third layer at the same spot as where the first layer is. This is what leads to the body-centered cubic, and it has a 68% packing efficiency. And going into what we considered closest packing, how do you kind of reconcile this? How would you do this? Well, you have 3 distinct layers as you do this. Try to focus mostly on the cubic packing in this class. There's also hexagonal packing, which is just slightly different, but we'll be really focusing on cubic packing here. And for your just for your information, these are very, very similar. The hexagonal closest packed and the cubic closest packed, or face-centered cubic, and they have the same efficiency of packing, which is 74%. Okay, so let's try another practice problem. Barium is the largest non-radioactive alkaline earth metal. It has a body-centered cubic unit cell and a density of 3.62 grams per centimeter cubed. What is the atomic radius of barium? And then it gives you the volume of the sphere is equal to 4/3 pi r cubed. Here's a roadmap of how I'm going to go about solving this problem. Okay. So if we take the molecular, one thing that the question's not giving us, it's giving us the density, but it's not really giving us the molecular weight, right? I guess in this case it'd be atomic weight. So that's what we're going to have to look up. So if we do molecular weight times density, something like 137.3 grams per mole divided by density, which is 3.62 grams per cubic centimeter. And we get 37.9 centimeters cubed per mole. Okay. We have to take into account the packing efficiency. So the bodied center cubic efficiency is 68%. So we take that number that we calculated and multiply that by that fraction 0.68, and we would get 26 cubic centimeters per mole. Okay, so that's the volume per mole. If we want to convert that the volume per atom, we just take the per mole volume divided by Avogadro's number, 6.022 times 10 to the 23 atoms per mole, and that will give us the volume of an individual atom. And now we want to find the radius of an individual atom. So we use our equation for volume of a sphere. We're just estimating the barium atom as a sphere. And we need to solve for R. And when you do that, you should get R equals the cubed root of 3 times volume over 4 pi. The other way you can write that is cubed root is to the 1/3 power. So 3 times volume here is, volume is 4 times 10 to the minus 23. And 4 times pi, pi is 3.14. And this is all to the 1/3 or the cubic root. And R, the radius of one of these atoms, would be 2.2 times 10 to the minus 8 centimeters. Okay. We have here on this slide, this is showing some dimensions in each of these packing arrangements. In the simple cubic, it's easy because your really only dimension is the length of a side, which is A. So A is just going to be equal to 2 times the atom's radius, right? This will be the radius of one of the atoms, okay? And it'll be that way in all of these, right? But now you can see that you can't really calculate A based on the radius and body center cubic because the 2 atoms at the corners don't touch anymore. So there's an extra little space there. Okay, so this figure kind of shows you how you would calculate that length of the unit cell based on the radius of the atoms. And you could use that to back calculate, if you knew the size of the unit cell, what the atom's radii were. Okay, and then finally for face-centered cubic, a little bit trickier as well. So let's try a practice problem with this. Copper adopts cubic close packing, and the edge of length of the unit cell is 361.5 picomolars. What is the atomic radius of copper? All right. So we're going to need to use a little bit of trigonometry here. Right? We have 2 sides, A and B, and a longer side, C. So this is where we need to know that relationship for triangles, right? We can find the length of C if we take the square root of A squared plus B squared. Well, in this case, it's a cube, right? So A equals B. So C is just going to be equal to the square root of 2A squared. And we're told A is 361.5 picometers, excuse me, 361.5 times 2 square that, and then take the square root. And hopefully I did that right. I get 511.2 picometers. Well, that tells us what C is, right? And, maybe we probably don't really care what C is. What we really care about is the radius of an individual atom. So if you look at C, there's one radius. There's two radius. There's a third radius. And here's a fourth radius. Okay, so C is going to be equal to 4 radii. So if you want to find what the radius is, you just need to divide C by 4. Well, how were these structures discovered? How do we know these crystal packing arrangements? And the answer to that is X-rays. Scientists use X-rays to discover molecular structures, how things are bonded together. And so now that was how the double helix of DNA was discovered, how protein and the alpha helix in the protein discovered in protein structures, and it's how these solid state crystal structures were also discovered. And these were actually some of the first molecular structures discovered because they are naturally forming crystals, and they were easy to shine X-rays at. And when you do that, you don't need to know very many specifics about this for this class, but you shine X-rays, and they interact with the atoms in the crystal lattice, and they will be diffracted, what's known as diffracted, so that it bends in, they point now in a different direction than they were going. Okay, so you can do this. You can have an X-ray source and put a very direct beam onto a crystal, and then you can look at it on a plate and get what's known as a diffraction pattern. And from that pattern, then you can build an idea of what that molecule, that crystalline molecule, what structure it has. Okay. And so again, this is a popular technique, especially the last 20 or so years, getting crystal structures of proteins. Okay. There's scanning tunneling micrographs. So this is of cesium atoms on a gallium arsenide, right? And so you can get other ways of getting molecular pictures shown here, okay, which kind of neat. Okay. So if we look at the types of crystal solids, well, you can have atomic crystals. So atomic, they consist of individual atoms, as the name suggests. They're held together only by dispersion forces. Molecular solids, you have individual molecules held together by various combinations of intermolecular forces, depending on the molecule. Ionic solids, those are consisting of a regular array of cations and anions held together by electrostatic force or ionic forces. Metallic solids, they exhibit an organized crystal structure just of metal atoms. And finally, network covalent solids consisting of atoms covalently bonded together in three-dimensional network. So atoms that are physically bonded together and not just held together by dispersion forces. You can have that as well. Here, a table that just shows some of their physical properties of each. You're not going to be tested over this, but in case you're interested. Okay, and just another figure showing some of these. We have argon, which would be an atomic crystal, and methane, CH4, which would be a molecular crystal. Okay, and they're both undergoing cubic close packing, or face-centered cubic. Sodium chloride. Sodium chloride is salt, table salt, and this is an example of an ionic solid where you have interchanging sodiums and chlorides, pluses and minuses in charge. So if you look at one sodium, let's just do this one because it's labeled, every vertice to it, it's going to be coordinated with a minus charge of chloride. Right? But if you look at the chloride, let's look at this one, every vertice it has is connected to a sodium. So they're interdispersed. And so if you do the space filling of that unit cell, you see that it's a face-centered cubic of chlorides, and the sodiums now are what would appear to be one in the center, right? And now you have an eighth of one on, or is that a fourth? No, that'd be a fourth. You'd have a fourth of one on each middle of each side. So that is a very tight packing unit cell. Zinc blende, the structure of that is shown here. This is a more complex structure. Now we have zinc and sulfur, S2- bonded together in this sort of network, covalent structure. And fluorite as well, calcium and fluorine, okay, kind of interspersed there, and you can see that these do get pretty complex, right? And here we have 4 entire fluorine atoms inside the unit cell, right? And the calciums in this case are on the corners and the faces, but not in the center. Metals solid pure metals tend to adopt more regular, I would say, packing structures. And so copper adapts this cubic close packing or face-centered cubic. Magnesium, very similar, except it's hexagonal. Okay, again, those differences between the two, how they differ, not important in this class. Just some comparison of diamond and graphite. Each of these is more of a covalently networked crystal structure, and diamond is harder and more resistant to breaking because it's has covalent attachments throughout 3 dimensions, whereas graphite, it's covalently attached in 2 dimensions, and then sheets of these stack on top of each other and have sort of these weaker intermolecular forces between the layers. So those intermolecular forces are easier to break. And so you can see the difference in some of the physical properties of that reflect that how much easier it is to break. We have the comparison between crystalline and amorphous silicon dioxide. So a certain molecule like silicon dioxide, it can have a case where it's a crystalline form or amorphous. Okay, the mineral crystallobite is the crystalline form of silica, which is silicon dioxide, and it uses cubic close packing in its unit cell. Quartz is the amorphous form of this, and it has generally disordered structure. Okay, so now we'll move on to discuss semiconductors. Okay, so that's another important solid state, I should say, call it a field in solid state chemistry or technology. Okay, and so if we look, trying to explain what a semiconductor is, if we look at just any metal, but we're going to use lithium now as our example, if you look at one lithium atom, you have a 2s orbital, one electron in it, and then you have these empty p orbitals. Okay, so lithium's a pretty easy metal to use because it has very simple orbitals to understand. Okay, lithium-2 now, we would mix the orbitals from 2 lithium atoms. So you'd have 3 times 2, which would be 6, and 2 times 1 would be 2. So you have double the number of orbitals. Now, you have 2 electrons because you have 2 lithiums atoms. So those both go in here, and now you have these empty orbitals. So you can keep doing this until you get to, if you had just like a solid chunk of lithium, you have a ton of lithium atoms there together, and they really act like they're all bonded together. It's a metal. And what you get is the orbitals that are occupied are down here, and that's called the valence band. And then all the orbitals that are empty are up here, called the conduction band. So in solid metals, electrons can flow freely through this conduction band. They just like hop between orbitals on adjacent lithium atoms and can flow from one side of the metal to the other side of the metal. They're essentially freely flowing. And so that's how metals can be used as wires for conductors, because electrons are going through this conduction band. So that how we would term a conductor. A semiconductor is a substance that is similar, but there's a gap between the valence band and the conduction band. So it's not as easy for electrons to move up into the conduction band and freely flow around. Right? And then what an insulator is a substance that gap would be a very large gap between the valence band and the conduction band. Okay, so semiconductors, again, have a small energy gap between them. So if we looked at pure silicon, it has an energy gap between the valence and conduction bands. Its conductivity is very low at room temperature. Right? What happens in semiconductor production is that these are actually what's known as doped. So other elements are added to silicon to create the desired properties. So one way you can do that is you can add something like phosphorus that adds an additional valence electron. Okay, these enter the conductance band and bridge the energy gap and increase conductivity. So you can think of adding something like phosphorus would add an electron, and that would be in the conductance band and increase the conductivity. These are called N-type doping or N-type semiconductor. Again, that N stands for negative for the added electron. You can also dope it with something like gallium, which removes electrons from the valence band. right? And so that, in that sense, silicon electrons can migrate to empty orbitals, which increases conductivity. And these are called p-type semiconductors, P standing for positive. Now, let's talk about that line in the periodic table, that sort of a staircase. And we refer to this as the metal-non-metal line. In general, everything over here are non-metals, everything to the left are metals. Okay. The elements along the line are called metalloids or semi-metals. And so things like boron, silicon, germanium, arsenic, antimony, these things are what we refer to as metalloids. Okay, metals are conductors, non-metals are insulators. Metalloids are where we get the semiconductors from. Right? And so Silicon Valley is named as such because silicon is used in semiconductors, which are needed for electronics. So if you place a p-type semiconductor next to an n-type semiconductor, you form a p-n junction. And in this p-n junction, electrons flow freely into the from the n to p direction. Okay, so the negative type semiconductor, those electrons can flow freely to the positive type semiconductor. For the rest of the lecture, we'll be talking about a little bit different materials and some more liquid materials. Okay. These are two structures that make liquid crystal phases. Okay. Don't need to know them. I wouldn't ask you to write them out or anything like that. But what they are, they're longer. They have these sort of aromatic rings on them, and they can stack together pretty well. And so they can stack in a number of different ways shown here, and order themselves in a liquid, but order themselves, have themselves very ordered, almost as if they were a crystal, but it's in the liquid phase. You can look in nature to see some liquid crystal type phases. Some viruses look sort of like this, very ordered. The actin and myosin filaments in muscle cells also look like this. Very, very ordered structure, but they're a very fluid molecule. Right. Another place where these are important are in LCDs or liquid crystal displays. Okay. And if you design this correctly, if you want to know all the pieces shown here, what you can do is have a case where if your current turns on, the molecules align and the light is blocked and make a dark region. So right, like a letter or a number showing up. Okay, and then if the current goes off, the molecules don't line up, so the light can pass through. Okay. So that's how you can make a display out of this. And this is a watch, so that's obviously a very simplistic display. Nowadays, you can make very high definition color displays using this technology. Right. We talk about ceramics at the end of this chapter, and here's just a few ceramics listed and kind of what their applications are. Silicon nitride, that's used in car engine parts, like some things like turbos. Cutting tools, a lot of cutting tools have ceramics. in them because they're very hard and very durable. Surgical implants, again, have ceramics because they're hard, durable. In ceramics, you do have not quite. There are, I guess you would call it crystalline bonding. It is more complex though, because a lot of these ceramic, their formula are just more complex than what we would consider for like a typical crystal, like a ionic crystal where you have a cation and an anion. These do get more complex, and their packing structures reflect that. Polymers. The polymers are another important class of materials. And what a polymer is just a repeat of something. So you have it's kind of like a crystal where you have a unit cell, but in a polymer you have just a mer, which is the smallest unit, and then you make a chain of that. Right? So instead of not necessarily in 3 dimensions like a crystal, but in 2-dimensional, like a 2-dimensional chain of something. Okay. And here are some names for some common polymers and their uses. And we use polymers every day of our lives. Okay. Plastics are polymers. And so you get this random coil sort of shape in polymer chains. So in this case, we have a hydrocarbon chain. This is polyethylene, and this is the black carbons and the blue hydrogens. So this is kind of what it looks like, and it will kind of randomly wrap around itself. Okay? And then you can heat it and mold them in particular shapes. So polymers, there's a lot of advantageous features and properties in polymers. And even within a polymer, something like the polyethylene, you can have regions of them that get very ordered, that have what we refer to as like crystalline regions. So you can have semi-crystalline polymers. Polymers would typically be sort of thought of as being viscous in aqueous solutions. One reason is that water can interact with the polymer if they can H-bond to the polymer itself and sort of stick the different chains of the polymer together. Viscosity would increase as more chains interact. Okay, so if you can have that type of interaction, this would increase the velocity quite a bit. There's also things called elastomers, which are like polymers, but they have an elastic sort of property to them. They are shown, some names of them are shown here, and their uses. Okay, the final thing we'll sort of talk about here are quantum dots. And quantum dots are what they are nanoparticles. Okay? They're nanoparticles, but they're of semiconducting materials. Right? And in particular, gallium arsenide or gallium selenide. So they're smaller, they're nanoparticles, which means they're small. They're smaller than 10 nanometers. The smaller the dot, the shorter the emitted wavelength. So that you can see up here the size. You have 2.3 nanometers to 5.5. And the varying colors, you can basically get all the colors of the rainbow out of these dots. Okay. And you can make nanoparticles of something that are magnetic. And so here we have nanoparticles of iron oxide. and this dispersed into a viscous fluid. And so you put this between the poles of a magnet, and you can actually see the magnetic field from these small nanoparticles of iron oxide. And somebody actually made a nanocar out of buckyballs. Okay, buckyballs are carbon that's in a C60, so 60 carbons that are in the sort of the shape of a soccer ball, right? And they attach that to some other hydrocarbon scaffolding, and they were able to drive it across this gold surface with the wheels actually like turning on the surface of the gold, and direct it with the atomic force microscope. So that's kind of crazy that the amount of material technology in materials chemistry it's pretty mind-blowing. So just wanted to kind of point out some of these aspects to you. We're not going to talk very much in detail about any of them. I'm not going to really expect you to know anything about any of those advanced materials, except semiconductors probably. That if you have to know one thing, I would pick that one. But it's a good thing to look at if you're interested in going into the materials field. Some of these things are very, very cool.